Please take the test before you check these answers. Score yourself honestly. Email me your score when you're done. Through satellites. So the first thing I want to do is just define an expression that relates the acceleration of a satellite A to its radius r, because that's what we're sort of comparing here. Well, it starts anyway from the force of gravity. This is Newton's universal law of gravitation. Is equal to gmm over r squared. But there's another formula for gravity, right? The one we used before we learned this one, the simple one, mg. And g was always 10, really it's 9.8 at the surface of the Earth, but it's not that value everywhere. That's why it's a lowercase, not a constant, or an uppercase constant, like an always true constant. G is better understood as g local, which is what I've written here. And that means the acceleration due to gravity at a particular location. So, since these are both expressions for gravitational force, you can set them equal to each other. And the m, little m anyway, cancels out. That would be the mass of the object moving in a circle or the satellite. So the only mass that's left in this expression is the mass of the Earth. Therefore, if one of these satellites has double the radius, you would plug in 2r in the denominator here, and then this is very much like that last question where you needed to make Cosmos' gravitational field the same as Earth's. You plug in a 2r, and then it ends up getting squared, so you double the radius, you quarter the acceleration. Straightforward energy conservation question. It'd probably be easier though if we just look at this. So I'm going to introduce an image to show what's going on. Center of mass is moving, and that's what the arrow V here is showing, is that its center of mass has a velocity, and therefore it's got two different kinetic energies. Kinetic energy rotationally and translationally. Then it's going to ascend this ramp and slow down at a constant rate while ascending, and then reach a maximum height. It comes instantaneously to rest, both rotationally and translationally, and therefore its only energy at the top is gravitational potential energy. So now we can set up an energy conservation analysis. Starting from the beginning, so kinetic energy translational plus kinetic energy rotational, and that's, again, that was on the ground down here while it was rolling without slipping, is equal to the gravitational potential energy at its apex on the ramp. Formulas for those things. And I also know that the rotational inertia of a sphere, this is in the prompt as well if you don't remember it, is 2/5 mr squared. So I'm going to plug that in for I, and also you'll notice here I've replaced omega, because omega is just velocity over r, or v equals r omega. That's the relationship between velocity translational and rotational velocity. That is all still equal to mgh, which is the gravitational potential energy at the top, and now there's an m in every term, and we have an r squared over r squared. So the m's and r's all cancel, and we end up with a height. If you go through and solve this algebraically, you end up with 7v squared over 10. We're asked to figure out what is the direction of the acceleration of these two positions. So starting from the bottom, this is the easier part. At point Q, the ball is no longer accelerating downwards. In a tangential way. It's no longer speeding up, because gravity was making it speed up from P to Q. But at Q, it has not yet begun ascending, but it has stopped descending, and so its speed is instantaneously constant, but it is still accelerating because it's moving in a circle. So it's got this centripetal acceleration, so the answer for position Q is upward, so it's got to be either C or D. Now we can try to figure out, should the acceleration at r be downwards or leftwards? Which one of those is correct? Well, at r, it's at the same height as p. And that means because it was at rest at p, energy conservation tells us that at r it will be at rest again. And that means at this moment, it will not have a centripetal acceleration. There's no need for any force to sort of pull it towards the center, because it's not sort of trying to go straight. It's stopped at this moment. So this centripetal acceleration is gone, only at that instant when it comes to rest. But it does still have a downwards acceleration, and the reason it has that is sort of the same as if you throw a ball up into the air. We've said in the past that at the moment it reaches its apex, it comes instantaneously to rest, but it is still accelerating at that moment. It's accelerating through its stoppage, if you will, because it has an unbalanced force due to gravity. And as long as you have an unbalanced force, you have an acceleration. Same is true here at point R. So the correct answer is C. This one requires us to know that, starting from Newton's second law, I guess is the best way to do this. Starting from F equals ma, the acceleration of an object is always in the same direction as its net force. Always. And in this problem, it doesn't say sigma F, but it tells us that the net force is just F. So when it says F, it means sigma F. Therefore, every F arrow has to be in the same direction as an A arrow. Any answer choice that doesn't satisfy that, you can immediately discard. Let's see. That takes out 3 of them. Okay, the last thing to consider here is whenever you're moving in a circle or in any curved path, you are accelerating. Even if your speed is constant, you are accelerating because your direction is changing, and direction is part of what velocity is defined as. So if you change direction, you change velocity, and you accelerate. And the only way you can make a circle or a curved path is you have to have an acceleration towards the center of that path. We call that a centripetal or a radial acceleration. And therefore, we need a net force and an acceleration that point radially, or at least have a radial component. So looking at answer choice D, force and acceleration are both tangential and therefore have no radial component. It cannot be B. So by attrition, it must be D, but let's make sure we understand what's happening here as well. So in D, F and A are in the same direction as our first condition, that they are direct proportions, but they don't appear to be coming radially. What's really happening here is that whenever we do circular motion, remember we use a tangential axis and a radial axis, which I just said at respectively. But what we want to look at is that there's two components, and one is the center, and we call that A sub C. Control acceleration. And then there's this other acceleration, which is in the same direction as the motion. In this case, we can get A sub T, or tangential acceleration. It's not asked for. I think it's important to understand that this question, the object is turning. That's what the control acceleration does. Also, the acceleration does it makes the same turn. This also changes speed. In this case, faster because it has a component of the addition in the same direction or parallel to the velocity. Question looks a lot harder than it is, but because you haven't learned simple harmonic motion yet, this is basically just a toss-up and a guess. As it turns out, the way you solve this question is there's a formula for simple harmonic motion that is sort of like the general formula for all simple harmonic oscillators. And I'm going to write it and then give you a very brief introduction to what it means, although a much more thorough introduction is on YouTube in playlist unit 10, simple harmonic motion, or whatever I called it. But anyway, so here it is. So it's x, or the position of something, is equal to x max, which is also known as the amplitude of something, or its maximum displacement from equilibrium, times the sine of omega t. And there's actually something else here, but it's not relevant, so I'm going to omit it. Okay, so that means that in both of these, the term in front of t is omega. That's 3 in both cases. Well, if omega is equal to 3, we have used omega in the past. We know that that's angular velocity. And therefore, if you're moving around a circle, you can think of velocity as distance over time, right? Well, delta theta is angular distance. We know we're using angular distance, right? Because this is an angular velocity, so we're just being consistent. And then that would be divided by delta t, the change in time. Well, if you go around one complete circle, and again, I'm only doing circles here because of the angular nature of these quantities. If I go around one complete circle, how far do I travel? 2 pi radians. 2 pi. Now, not 2 pi r. 2 pi r is the circumference. That's the linear distance. So this is just 2 pi. And then the time, how much time does it take to complete a circle? T. That's the period of a circle. So we end up with 3 is equal to 2 pi over t. You can just solve this for t, which is again the period, and that's what you asked for, and you get 2 pi over 3. Same setup, new question. We're asked for the speed of the particle. This one you can actually do without knowing a single thing about circular motion or simple harmonic motion. All you need to know is that these are position functions and you're looking for a speed. So if I were to say to you, how do you go from a position function to speed, you could answer that. You just take the derivative. The only twist is that we're not given a single function for position. We're given two functions. One is in each dimension. So since I have two different functions, one in each dimension, but I'm asked for the total speed, we need to remember how to do that. So the total speed, v, is equal to the vector sum of the component of speed in the x dimension and the component of speed in the y dimension. So I'm going to start in the x dimension. Since I have a position function, I'm going to take the derivative with respect to time of 5 cosine of 3t. And this is going to be a chain rule thing. So the derivative of the inside, 3t, is just 3. And then that gets multiplied by the derivative of the outside, which is 5 cosine of term, 5 cosine of argument. And the derivative of cosine is negative sine. So you simplify this to negative 15 sine of 3t. Hold that thought. In the y dimension, we have the same basic approach. We have the position function, we take its derivative, and we get 15 cosine of 3t. Now we need to sum those two things. This is vx, right? That's vx in this equation, and this is vy, and that's this vy. But we need to sum them vectorially. You're not just adding them, you're adding them as vectors, which means using Pythagorean theorem because these are in two different dimensions. One is x, one is y, and you have two sides of a right triangle. You're looking for the hypotenuse. So Pythagorean theorem, a squared plus b squared equals c squared. I've just jumped ahead one step and I've solved this for c. So like instead of being c squared, you know what, let me make sure it's clear what I'm talking about. So like back here in the original equation, if you're adding these vectorially, really what I'm saying is c squared is a squared plus b squared. And if you take the square root of both sides, you can solve for c, which is the total velocity. That's what I've done here. Something really interesting happens now. This looks like a complicated mess, I'm sure, but it's a lot easier than it might seem, and here's why. You can factor out sine squared of 3t plus cosine squared of 3t, this whole term. And the sine squared of anything plus the cosine squared of the same thing is 1. So all you end up with is 15 squared times 1, and the square root of all that is just 15. This problem is probably easiest to do in sort of a proportionality way. Let me show you how I might set this up. Starting from the law of universal, you know what, let me just make a point here because I realize this as I go through these solutions. Every time you see like astronaut or satellite or orbit, those are like your key words. You're going to almost always use this equation, right? The law of universal gravitation. So from this law, this is one expression for gravity, and here we have the other expression for gravity. We talked about this in that slide with the two satellites of different orbital radii. But what we can do is we can set these two different expressions for gravity equal to each other. Little m is going to cancel out, which is the mass of the orbiting body, like the satellite's mass. And the only mass that remains is, once again, the mass of the Earth, or the planet at the center of the orbital path. And therefore, g local, and that's the acceleration due to gravity at a particular location, is equal to gm over r squared. And r squared, well, on the Earth, we know that distance is 6,000 kilometers. That's in the prompt. We are going up another 300 kilometers. How much did we increase the radius? From 6,000 up to 6,300 is a 5% increase. Feel free to check the math on that, but it is. And so if you increase the value of r by 5%, and this, g local, is 10 on the Earth's surface, you can just do 10 over 1.05 squared. 1.05 being a 5% increase in my r value. And 9.07 is the precise answer. Nearest answer choice is therefore 9.